These are the 6.3 Part 2 notes. This is finishing up binomial random variables, and we're going to look at geometric random variables as well, which there's really not too much to talk about in geometric random variables. All right, so the last part of binomial random variables is the 10% condition and the large counts condition. And again, just like with 6.3 Part 1, please read your book. Your book is going into a lot more detail on why these formulas work, why we can look at these rules. I'm going to give you a verbal description, but the actual numbers are much better defined with really good examples from the book. We can use a binomial distribution to represent a non-binomial distribution of samples taken from a larger population, because sampling is done without replacement and probability isn't the same. If the number n we take out of the population is less than 10% of the population, we can still represent this random sample via binomial distribution. So the entire concept here is that when we sample from a large population, it is done without replacement, so therefore each and every trial actually doesn't have the same probability. But when we are taking less than 10% of the population, the difference in the probability is actually a lot smaller than one would be led to believe. So like the difference between 100 or let's say that we had like the difference between 99 out of 100 and 98 out of 99 is not incredibly different. The difference between 1,000 out of 10,000 and 999 out of 9,999 is not that much different. The difference between 50 out of 100 and 49 out of 99 are not that much different. We're talking about really, really small changes. So if we can pull less than 10% of a population out for our sampling, well, then we can use a binomial distribution to represent it. Because again, like if we're working on the orders of thousands and we're looking at the entire United States population, well, that's a very, very, very small difference in the overall probability done without replacement from the probability done with replacement. So we can just say, all right, we're going to do a binomial, we're still going to use a binomial random variable here because it's not a perfect binomial random variable, but the difference that exists by doing this as the same probability with every trial as if we were doing this probability with replacement versus doing this as a probability without replacement is so fractionally small that there's no need to go in and do this calculation every single time. So if we're talking about like a sample of 1,000 and we're using census data and we have the entire country and we're trying to figure out what's the probability of 1,000 randomly selected US adults representing this, like having this in common or having this trait, we can just use binomial distribution given the probability of the entire population. We're not going to go through and set up each probability changing as we do this without replacement. And that's just something to make life a little bit easier because numerically speaking, the difference is so small, it doesn't really matter. This is one of the nice things about statistics versus like, let's say calculus. We're not doing this, we're doing this, like this data does matter. It helps with scientific experimentation and that definitely matters. But like if we're doing this for marketing data, if we're doing this for like sociological trends, if we're doing this for things like that, it doesn't matter nearly as much. If we're doing this as like we're a company and we're looking at a small sample of our product to just quality test it to make sure that the last batch meets company standards, we don't need to concern ourselves with what is the exact probability. If we are within a close enough number, we're good. That's one of the nice things about statistics versus calculus, where calculus you have to be exact. If you're not exact, the rocket's going to explode. Everything's going to go wrong, and astronaut lives are on your hands. In statistics, astronaut lives are not on your hands nearly as much as possible. Companies' profits might be extremely important, but those companies' profits can, it's not going to be the world's biggest difference over whether or not a sample is perfect or not. All right, now the normal approximation rule, the large counts condition, we can use a normal approximation for a binomial random variable if our mean of that binomial random variable is above 10 and our standard deviation is above 10. So both your mean and standard deviation have to be above 10, and then you can use a normal approximation for your probability. And you don't have to go through the process of plugging in numbers and using that like binom CDF feature of your calculator. So if we're talking about like we've got a sample size of 1,000 and our probability is like 0.4, so your mean is 400. And in fact, let's just talk about that. Let's just say that we've got a sample of 1,000. We've got a probability of 0.4. That means our mean is 400. Your standard deviation would be the square root of 1,000 times 0.4 times 0.6. So just doing the calculations here. Your standard deviation here is 15.5. Okay, cool. So now I can just go ahead and, as opposed to like having to do calculations every single time, if I want to figure out what's the probability of less than 700 people having this condition, or what's the probability of more than 700 people having this condition, I can just go ahead and I can use table A, I can use z-scores, I can use the normal distribution feature on my calculator. I can do all of those things, and I can just go back to a normal distribution. So when we have really, really large counts of a population size to the point where our mean is above 10, our standard deviation is above 10, and we are looking at a binomial random variable, well, then it's a normal distribution. Or we can use a normal distribution to approximate the probability of that binomial condition. All right, so now we're going to talk about geometric random variables. A geometric setting arises when we perform independent trials of the same chance process and record the number of trials it takes to get one success on each trial. The probability P of success must be the same. So this is very similar to a binomial random variable. The difference between a binomial random variable and a geometric setting is the number of trials. So that's the only difference. They still both have to have only a success or a failure. We either have to define success or failure. We can't have both. You have to have a success or a failure. It has to be independent. Every single time that we do this has to be independent, and then every single independent time has to have the same probability. So like you can't draw cards until you get an ace, because that's done without replacement. If you're doing things with a card deck with replacement, then it could possibly be geometric. But you have to have it independent with the same probability every time. Only difference is now we are not talking about, we're not setting a number of trials and seeing how many successes we could get in that trial. We're saying, all right, we have an endless number of trials to get to a success. How many trials is it going to take us to get to that success? That is the difference between a binomial random variable and a geometric variable. So the book is pretty straightforward of that a lot of these formulas, it breaks down how the geometric probability formula works, kind of showing you through those probability trees, how we can create this equation for the geometric probability. I like the fact that the book kind of just shows you that the mean is the inverse of the probability, and then I love how it says that standard deviation is beyond scope of this class. So geometric random variables have a little bit of advanced mathematics, but we can start looking at the basics. We can look at what is the probability of something occurring on a specific trial. We can look at the what the mean number of times to get there is, so on and so forth. So we've got our formula here. If we're looking at a geometric probability, if we're looking at something that's within the geometric setting, and the probability of something happening on the k time, it's equal to 1 minus the probability to the k minus 1 times the probability of it occurring. And then the mean is just the inverse of whatever is the reciprocal of whatever the probability is. So we just take the positive reciprocal of the probability, and that's your mean. So let's go ahead and look at this. Suppose you roll a pair of fair six-sided dice until you get doubles. Let t equal the number of rolls that it takes. So we know that doubles, so show that t is a geometric random variable. I'm just going to go through this verbally. So number one, this is independent. Every single time we roll the dice is not influenced by the previous time we roll the dice. These are independent trials. Number two, we've got a success or a failure defined. Yes, we have got 6 different conditions for success, but our success is very clear. It's either doubles, and then our failure is not doubles. So we can clearly define one success, one failure, and that's all it is. And every single one of these independent rolls is the same probability. We know that doubles occurs on 6 out of the 36 possible combinations of rolling 2 die. So every time that we roll 2 die, we've got 36 possible combinations, and 6 of them are doubles. So we know that we've got a 1/6 probability of it occurring. And we are going to do this until we are successful. We have not set a specific number of trials. We want to do this until we get the right number of trials. So when we look at the probability here, find the probability of t being equal to 3. So what's the probability that we get doubles on our third roll? Well, the probability of your doubles happening on the third row are going to be equal to this formula up here of 1 minus 1/6 squared, because that's 1 minus the probability times the, or to the power of the number of times we're looking at, minus 1, multiplied by the probability itself, which is 1/6. So this is equal to 5 over 6 squared times 1/6, 25, 36 times 1/6. And this is equal to 0.1157. Thinking ahead here. So you've got an 11.57% chance of your first roll, or of your first doubles, happening on trial 3. So this means that you roll, you don't get doubles, you roll again, you don't get doubles, you roll a third time, you get doubles. That's what that means. That's what it means in context. All right, so in the game of Monopoly, a player can get out of jail free by rolling doubles within 3 turns. Find the probability this happens. So you might be tempted to say that this is the probability t is equal to 3. It's not. It's the probability t is equal to, or is less than or equal to 3. So what is the probability? Because if you roll doubles on your first turn, then you're golden. You've got it done. It's all over. If you roll doubles on your second turn, you got it. If you roll doubles on your third turn. So this is actually going to be the probability of 1 plus the probability, or the probability of t is equal to 1 plus the probability of t is equal to 2 plus the probability of t is equal to 3. So I've got 5/6 to the 0 times 1/6 plus 5/6 to the first times 1/6 plus 5/6 to the second times 1/6. And I'm just confirming my formula. Yep. So I'm just going to plug all of this into my calculator. So I've got 1/6 plus 5/36 plus 200 are 25, 216ths. So this is equal to 0.4213. So you've got a 42.13% probability of rolling doubles on your first term. So you've got, or within your first 3 turns, because you've got that 1/6 probability of rolling it on your first turn, which is your greatest probability. You got 5/36 because you missed it on your first, but then you got it on your second, and then so on and so forth, thinking in terms of that probability tree. We're just kind of skipping making the probability tree and going all the way out. So our probability of getting it by the 3rd turn is the addition of every single turn of those first 3. What's our probability of getting it on 1, 2, or 3? We add those all up, and that's our probability of getting it within those 3 turns in this geometric setting. Now, the mean here is going to be 6. We've got a mean of 6 doubles, or 6 rolls that we would have to get a success of 6 doubles, or of a double. In order to get a double, we'd have to roll this 6 times for our average number of times rolled to get a double. And that makes sense with this 1/6 probability of getting there. All right, you guys got a homework assignment tonight. If you have any questions or concerns, reach out as soon as possible, and have a great night.